today we'll be looking at the three Pythagorean means. So first off, we have the arithmetic mean, which is the most commonly used and most commonly known. It's just the sum of all of the integer values divided by how many values there are. So if the values are 3, 9, and 12, it'll be 3 plus 9 plus 12 all over 3. The arithmetic mean finds the mean of a data set, which is just denoted as x bar, and it's a general use formula for finding central tendencies. The geometric mean is the nth root of the products of all your integers, so it's very useful for multiplicative relationships, most notable of which would be exponentials and compound interest. Those are the most notable uses of the geometric mean. And the harmonic mean is the number of scores on the sums of the reciprocals of the integer values. And this is useful for both multiplicative and divisory relationships, most notable of which would be rate of travel, for a good example. The first statement that we're going to look at for proving the relationships between these means is that the harmonic mean is always the reciprocal of the arithmetic mean of the reciprocals. I stress always because that's a for all statement. It means that one counterexample will mean that it's false. So using three lots of numerical values, you can see that for -3, 1, and 2, the arithmetic mean equals about 0.38 and the harmonic mean about 2.57. Those values do match with what the statement wants. 1 on 0.38 does equal 2.57. With 11, 12, and 14, same thing. 1 on 0.08, which is what the arithmetic mean is, does equal 12.21, which is the harmonic mean. 0, 3, and 5. So with this statement, you get undefined with both the arithmetic mean and the harmonic mean. However, 1 on something that's undefined is still undefined. So given that the arithmetic mean and harmonic means are both undefined, 1 on the arithmetic mean still does equal the harmonic mean. So therefore we can deduce that the statement is true, as we have negative values, we have positive values, and we've tested 0 values. Our second statement for the relationship between the means, we have that the general mean is less than the arithmetic mean for any set of 3 integers. Again, stressing any as it's saying that it's a for all statement. So using the numerical substitutions of 7, 8, and 11, you have the arithmetic mean equals 8.6 repeater, and the geometric mean is approximately 8.51. Now 8.6 repeater is greater than 8.51, hence the arithmetic mean is greater than the geometric mean, and it proves our statement. Since geometric means have a problem with 0, as anything multiplied by 0 will equal 0, it's interesting when you put in 0 values. So the arithmetic mean of -3, -1, and 0 is -1.3 repeater, but the geometric mean of -3, -1, and 0 is 0. Now -1.3 repeater is less than 0, so the arithmetic mean is less than the geometric mean for that set of integers. Now since it is a for all statement, one counterexample disproves it. So that one example where the geometric mean was greater than the arithmetic mean disproves that statement. So negating that statement gives us there exists a set of 3 integers such that the geometric mean is less than the arithmetic mean. The third statement that we're going to have a look at in the relationships of these 3 means is that the harmonic mean is less than the geometric mean, granted that any value of x as an integer is greater than 0. So we'll substitute in some values to check this. So 1, 2, and 3. the geometric mean will equal the cube root of 1 times 2 times 3, which comes out at about 1.82. The harmonic mean will equal 3 on 1 on 1 plus 1 on 2 plus 1 on 3, which comes out as about 1.63 repeater. And here 1.82 is clearly greater than 1.63 repeater. Therefore, the geometric mean is greater than the harmonic mean, which upholds our initial statement. Testing another set of values, we have 3, 54, and 212. The geometric mean will equal the cube root of 3 times 54 times 212, which comes out as about 32.51. The harmonic mean will equal 3 on 1 on 3 plus 1 on 54 plus 1 on 212, which comes out as about 8.41. Here 32.51 is clearly greater than 8.41, and therefore again the geometric mean is greater than the harmonic mean. Now, seeing as our restriction is that our integer values have to be greater than 0, judging by the two values that we've already put in, nothing's going to change. The geometric mean is still going to be greater than the harmonic mean, and we have no ways of determining that it isn't. Therefore, we have to conclude that this statement is in fact true. The harmonic mean will always be less than the geometric mean, granted that the integer values of x used are greater than 0. For the last of the relationships between the Pythagorean means, we're looking at the statement that the arithmetic mean equals the harmonic mean when x1 equals x2 equals x3 and x is an integer. So substituting -7 as all three numbers gives us the arithmetic mean equals -7 and the harmonic mean equals -7. So the arithmetic mean equals the harmonic mean and upholds our statement. Substituting in 9 as all the three values gives us that the arithmetic mean is 9, the harmonic mean is 9, so the arithmetic mean again equals the harmonic mean. But if we substitute in 0 as the three values, which is where the harmonic mean struggles due to 1 and 0 being undefined, we have the arithmetic mean of 3 zeros being 0, but the harmonic mean being undefined, so the arithmetic mean does not equal the harmonic mean. Since this is a for all statement, the statement has been proven false. So we have to negate it. And this negation gives us there exists values of x, x1 equals x2 equals x3, and x is an integer, such that the arithmetic mean equals the harmonic mean. Stating the relationships between the sizes of the three Pythagorean means, we get that the arithmetic mean is greater than the geometric mean is greater than the harmonic mean for x is greater than 0, as when x equals 0, the harmonic mean is undefined and the geometric mean will always equal 0. We can come to this conclusion by linking question 2, part 2 and 3 together. And another relationship of the sizes is that the arithmetic mean equals the geometric mean if and only if, that's what that shorts for, if and only if x1 equals x2 equals so on and so forth equals xn. So here we're trying to prove that what we stated in question 3 is true, that the arithmetic mean is greater than the geometric mean is greater than the harmonic mean. So what I've done here is I've gone into 2 steps. So I've tried to prove first that AM is greater than GM and gone through all of that, so we'll go through that. So the arithmetic mean is a plus b on 2 is greater than the square root of ab, and since the inequality only holds up if the values are greater than 0, a and b have to be specified that it's greater than 0. We square both sides to get rid of the square root. We multiply both sides by 4 and expand out the a plus b all squared. Then we take 4ab off both sides to get a squared minus 2ab plus b squared is greater than 0. And then we factorise for a minus b squared is greater than 0. And that is a true fact. That's a known fact. Any number squared will be greater than 0 if they're not equal. So from that proof, AM is greater than GM. Next, we prove that GM is greater than HM. So we have the square root of AB is greater than 2 on 1 on A plus 1 on B. Again, A and B are both greater than 0. For the first two steps, we just simplify the fraction of 2 on 1 on A plus 1 on B. And we arrive at square root of AB is greater than 2AB on A plus B. We square both sides, and then we multiply by A plus B squared to get AB outside of A plus B all squared is greater than 4A squared B squared. And then we expand out the bracket to get A cubed and then multiply by AB to get A cubed B plus 2A squared B squared plus AB cubed is greater than 4A squared B squared. We take 4A squared B squared off both sides. We factorise, so we take AB out of everything to get AB outside of A squared minus 2AB plus B squared is greater than 0. Divide by AB, so we'll get rid of that, and then factorise again to get A minus B all squared is greater than 0, again, which is a known fact. And we can link these two proofs together to arrive at AM is greater than GM is greater than HM for AB greater than 0. Okay, so lastly for question 5, we're using the arithmetic mean geometric mean relationship to prove inequalities. So that relationship is that they both are equal to each other if and only if all of the integers are the same. So x1 equals x2 equals so on and so forth equals xn. And we can use that by substituting in for an unknown value, using that relationship to make all the integers the same, and then evaluating that, getting a value, and then resubstituting that back into the initial equation. So for this question, we're finding the minimum value. So we'll let y equal x sine x. So this will mean that this will equal 5 plus 20y squared on y, which equals 5 on y plus 20y. Now, 5 on y plus 20y will equal 2 root 5 on y times 20y, if and only if 5y equals 20y. So 5 on y equals 20y. Just skipping a few steps here, we'll get that 5 on 20 equals y squared. Now, x is greater than 0, and sine x is greater than 0 from our initial assumption. Therefore, y is greater than 0. So y equals root 5 on 20, which equals a half. And we'll resubstitute this back into the formula. So sub into 5 on y plus 20y. So we'll get 5 on a half plus 20 times a half equals 10 plus 10, which equals 20, and 20 is the minimum value for that function.